Okay, so the next thing we need to look at in regards to digraphs is how the adjacency matrix C is going to work. So let's just write that adjacency matrix, and let's remind ourselves on how it worked with, just a normal graph. So with a normal graph, we had our vertices, written there like that. I'm going to keep this very, very small. So we had our A, our B, and our C. And I'm just going to leave it like that. And then we had a situation of, if it was connected, if A was connected to B, we wrote 1. And if A was connected to C, we wrote 1. And we also did, a very similar thing over there. We have the zeros occurring there and zeros there. So we had the 1, we had A and we had B, and we had A and we had B was 1 and 1 because we had no direction. Now we have a direction, so we're going to actually have to be very careful about that. So we are going to restructure it just a little bit by saying that let D be a digraph of order n. We're still going to have the adjacency matrix C as an n by n matrix. So we still have, that situation where your Aij is equal to the number of edges Vi Vj, which is the element of Ej. Now, there is a reason why I write it like this instead of, very specifically with the whole 1 situation with the number of edges, and that is just to incorporate the various digraph definitions. So we'll be working with simple digraphs, but you can get digraphs where you have situations of A goes to B, so you have parallel edges. So I'm thinking about situations like that. I'm also thinking about situations where you have like a loop situation, and that kind of like, so the loop goes to A. However, let's just be very, very clear of what it looks like in a simple digraph. So for a simple digraph, we still have this part, we still have this part, and then we're going to restructure this here. So we're going to be like where Aij is equal to 1 if VIVJ is an element of the edge set, and 0 otherwise. Okay, so we have the adjacency matrix C, particularly so that we can fit in or incorporate parallel edges and so on. However, if we narrow it down to the simple digraph, in other words, there are no parallel edges, there are no loops, it breaks it down to 1 and 0. And 1 only if your Vi to Vj is an element of the edge set. And now, so previously when we had this, normal graph situation, AB was equivalent to BA. This is no longer like the case here. So when we have our digraph and we have, say for example, A, B, and C, it's very specifically AB, it is not BA. So you will fill in with your AB as 1, but not your BA as 1. So let's actually go ahead and do an example of this. So let's draw this. So we have A, and let's have A going both ways, just so you can see what happens in that regard. And then let's have C, where it only goes in one direction. And then let's just have B there. So we have just, a small-ish graph. So we're going to have an adjacency matrix C, so that's A is equal to, and now I'm just going to put in A, B, C here, and A, B, C, just so you can remember what's going on. Okay, and then you'll have, obviously, your matrix C will come like that. So now we look at it, and we go, okay, let's start with A. We have an AB edge, we have an AC edge. So we have 0, 1, 1. Then let's look at B. So if we look at B, we have a BA edge and we have a BC edge. So we have 1, 0, and 1. Then we look at C. So C has, and when you look at this, you don't start from C anywhere. There is no edge that begins at C. So 0, 0, 0. So when you look at this, you go from your A, you look at this A, and where does it go to? So from to. So previously it wasn't that big of a deal, but now you have a from situation. So you have your A is your VI, and your B is your VJ. And if your VI to VJ situation, it's going to be that one there. So from to. Okay. Now, we have an adjacency matrix. Can we work out the sum of, well, can we work out the in degree and the out degree from the adjacency matrix? So we have an adjacency matrix. It's sitting over here. Let's just clean up some of the stuff here. Can we work out the in degree and the out degree? So if we look at this and we sum up the rows, we have the degree of something of A is equal to 2. Here we have the degree of something of B is equal to 2, and the degree of something is equal to 0. So again, remember we said this was from and to. So it should be the out degree here. So when we're thinking about this, it's the out degree. So remember, the out degree is going, from that vertice radiating outwards. The way that we set up our adjacency matrix, when we do this, we have our rows represent where it's from, and then our columns represent where it's to when we, writing everything down, which means when we sum up the rows, it is giving us our out degree. And that also means when we're summing up our columns, it's going to give us the in degree because it's the to situation. So the ones at the bottom, this will be the degree minus of A is equal to 1, summing up, the column. The degree minus of B is equal to 1, and the degree minus of C is equal to 2. And again, it's because we have, our rows representing the from and our columns representing the to, so we can easily see where exactly to get that from. So summing up the rows gives us our out degrees, and summing up our columns gives us our in degrees. And that is it for digraphs. Just be aware that digraphs are very, very important in real life situations because obviously a lot of life situations have direction involved in them. And one of the things you can do now is you can go play your breadth first search and your depth first search now on your directed graph, taking into account that now when you perform the search, so say for example, let's just go into fresh page.